Welcome into the beginning of Calculus 3. And before we can even start with calculus, we got to get used to what? Living in 3 dimensions. Right? So let's not use this color. 3-dimensional space. So we'll just say 3D. Right? So starting off, when we started first our algebra days, we were living in 1 dimension, R. And that just looks like a right number line. Then, moving forward in the world, right, we decided to add another dimension, and this is where we've been performing all of our calculus thus far. Right, so what does R cross R look like? Well, it's just R2. Kind of straight. And now, moving into 3 dimensions. Right, R cross R cross R. Right, well, this isn't a very efficient notation, right? So if we're living in like R10, you could imagine this would not look pretty. So let's go ahead, we're gonna abbreviate it, right? We're living in R3. And now where is this 3rd dimension? Well, it is this line here. Now, so we can make sense of it, I know it's not very even, right? Imagine this line here, I'm traveling at you and away from you, at you and away from you, right? We're going to call this one X. Now, this line here, right, self-explanatory, the other two really, but I'm traveling right and left, and we call this one Y. And now up and down, we're going to call this one Z. Right, so now we have our X, Y, and Z. Right, not too bad. Okay, and what I wanted to get used to, or us thinking about here, is this is 3 different planes, right? And I'll write them out here. This is our XY plane. And again, I'm going to have there'll be a graphic that comes up over here on the right. But imagine our XY plane. So we're only traveling, let's say I'm on my apartment floor, I'm only traveling on this floor, I can't move up or down, right? This would mean Z is equal to 0, right? I can't move up or down. I'm only living, right, in my XY plane. And same thing, right? Let's say XZ plane. If I'm only living in my XZ plane, I can't travel in my Y direction, so I can only walk towards you, go backwards, jump up, go through the floor, right? We'll say Y is equal to 0. And maybe we see the pattern unveiling here, right? If we are in our YZ plane, I can't travel in my X direction, right? So X is equal to 0. So we have these 3 different planes intersecting with each other. Right, now we have one other thing, or we have a few other things to discuss before we take a short break. But in R2, what were we graphing? So eventually we're going to get to graphing things here. So in R2, right, we're graphing curves. Right, think about R3 though. Now we're living in a 3-dimensional space. We're going to be graphing surfaces. Right, and we're going to do a few examples here. And I'm not even going to attempt to try to draw my planes here in a second, but there'll be some graphs that come up for you guys to visualize. And so let's say, let's give an equation here. Let's say Y is equal to 5. All right, Y is equal to 5. What do these points look like? Right, I have 3-dimensional points here. They have X, Y, and Z coordinates. What do my points look like? Well, my X coordinate, right, can take on what values? Negative infinity to positive infinity, right? So I have no limitation as to what I can plug in for my X. My Y value, I am constrained to just 5. And my Z values, right, again, any value that I want. So this is what my points, all of my points look like, right? So what we end up having, right, is we're going to be Y is equal to 5, but we're going to be a plane, right? Think about like a piece of paper is like a plane, like a flat surface, but it's going to be parallel to my XZ plane. Okay, I'm going to do one more. It might help. Maybe I've confused some people because we went with xz first. Let's go ahead and try, we'll do z is equal to 3. Right, so this is going to be a similar idea, right? What's happening? My x and y, I can be whatever I want. I'm constrained to only z values of 3. Again, I'm going to be a plane parallel to my xy plane. So I'll give you an example here. So imagine we're all on the 0 floor, we'll start with 0, of an apartment complex, right? So we're walking around the bottom of the apartment complex, we're on the 0 floor, I can travel in my xy plane, my z value there is 0, right? Now I take the elevator up to the 3rd floor, I'm stuck on that floor, the 3rd floor, and I can walk around wherever I want, right? So notice how those two planes, the 0 floor of my apartment and the 3rd floor, are parallel to each other, right? That's what we're looking at here. Again, I'll put another graphic so you guys can see, right? So this is what planes look like when we're dealing with 3-dimensional space. Let's go ahead. I want to introduce one more thing before we take a break, just so we get an idea of one type of surface. So let's use an equation that hopefully we're all familiar with. Let's say x squared plus y squared is equal to 1. Right? Well, in 2 dimensions, we know what this looks like. This is a circle, right? I'm going to add another constraint. Let's say z is equal to 3. Right? So this means I need to go up 3 floors. 1, 2, 3. And I have a circle, right, around z is equal to 3. Right? In which the radius here is 1. Right? So if I constrained everything, I constrained my x and y so that I'm a circle. I've constrained my z, so my z values have to be 3, right? So I have a circle around, right? It's around z is equal to 3. Or around, sorry, the z-axis. Okay? Now, this is a very special case because what happens if I get rid of this? What happens if I get rid of my z is equal to 3? Take a second, think about it, pause the video. Okay, you're back. If I have no constraint anymore on what my z values can be, I can be any z value that I want, right? My restrictions are solely on my x and y. That means I can travel up and down, right, on my z. So instead of having a circle in 3 dimensions, this is my best attempt at a cylinder, right? This is a cylinder. Good enough. You get the idea. All right, so I have a cylinder. Okay, so we're going to pause at this point. Coming back, we'll talk about distances between points. We'll get a little bit more familiar with points in space as well as distances, and we'll go from there. All right, see you guys. Jumping back in, I want to talk about the distance formula in 3 dimensions, and we're kind of just going to derive it, right? So this part of the video might seem boring, but we want to see where the distance formula in 3 dimensions comes from. So I'm going to make my xy graph here. And we'll say, again, this is x, right? This is y, this is z. All right, now I want to choose 2 points. Now I'm going to pick the point at the origin just because it's the easiest for me to draw from. All right, feel free to pick other points if you want to do this drawing, but I'm going to call this one P1, and I'll pick some point over here. Let's just call this P2. Right, so we're just going to draw a line connecting them. And the notation that we're going to use for the distance between these 2 points is just going to be some bars. Right, so this is our interest. Now what can we do here? This is coming back from the Pythagorean theorem, is we can construct a triangle. So we're going to draw a perpendicular line straight down from this point into the xy plane. Right, so it's dropping straight down, close to straight down into the xy plane. And over here, right, we're just going to finish out this triangle. We're going to call this point over here point B. All right, so now let's apply the Pythagorean theorem using the points that we have. I understand we don't know what B is yet. Right, so, well, what is this saying? The distance from P1 to P2, right, this is the hypotenuse. Because we drew this line straight down, this gave us this right angle here, right, close enough, right? So that P1, P2 squared, the hypotenuse, is equal to the distance between P1 and B squared plus the distance between P2 and B. Now, P1 and B is still a little bit mysterious. We don't know what it is exactly, but P2 and B, what is happening here? Well, we took our z value and just dropped it straight down, right? So this here, the distance between P2 and B, right, is just going to be the distance between our z values because we drew a straight line straight down. It's keeping the same x and y values. The z value here is just changing, right? So let's write a key on the side over here. We'll say P2 to B is just equal to the distance between our z's. Right, so that part is taken care of. P1 and B, though, I don't know what that is. But again, what I'm going to do here is I'm going to create another triangle. So I have one triangle here that helped me find the z value. That's going to help me with this piece, right, the difference between the z's. But P1 and B, I'm going to create another triangle. Right? You can imagine if I took this point here and drew a straight line across, right? This is going to form another right angle, and we're going to call this point A. Okay? And so now we can form another Pythagorean, right? Use the Pythagorean theorem one more time to find what P1B is. So we know, let's use a different color here, P1, and let's draw a little line here, P1 to B is equal to, or squared, is equal to the distance from P1 to A squared. And what is P1 to A? Well, P1 to A is just the distance on our x values, right? So P1 to A is just the difference between our x's. Okay, that's helpful. Plus A to B squared. Well, what is A to B? Well, A to B is just going to be the difference of our y's, right? So we'll write this here. A to B is the difference between our y values. And so what do we get, right? Well, let's put both of these equations together, right? Because we want to solve for P1, P2. So P1, P2 squared is equal to, and let's just go down the list here. Well, P1B is going to be this. A, B, sorry about the squeaky markers, plus P2B good. And now we'll make this substitution as well, right? We know that P1A is again the difference of our x's. Let's see if we run out of space here. Plus A to B is going to be the difference of our y's. Plus P2 to B is the difference of our z's. And what do we want to do to solve, right? We don't want the distance squared. We just want to take the square root, right? So the square root here is going to be the distance P1 to P2 is just going to be the square root of x1 minus x2 squared plus y1 minus y2 squared plus, finally, z1 minus z2 squared. And that is our distance formula. So very similar, obviously, to our distance formula in 2 dimensions, just adding on the z values, but I wanted to make sure we understood the derivation. I know my drawing's not perfect, but I will try to add a graphic if I can. Right, so all we did was construct 2 triangles and utilize the Pythagorean theorem twice. Now essentially this is the same for finding the equation of a sphere. I'll introduce it briefly as we enter the next video. All right, I'll see you guys soon. Okay, so quickly, I just want to introduce the equation of a sphere. So this part of the video will be fairly short, only because we did most of the legwork in the previous, distance formula, equation of sphere. Now I'm going to do my best attempt at drawing a sphere here. There also will be a graphic in the right-hand corner that pops up. So again, we need our xy coordinate. Or not xy, this is technically the yz. And then we'll add our x's in here. And again, for my drawing's sake, because I'm not great at drawing in 3 dimensions, I'm just going to make this as easy as possible. I'm going to start my sphere at the center. Okay? And what we say, we labeled the center. I'm going to label it C here. But C has the coordinates of H, K, and L as the center. Right, and let's go ahead, and I'm going to do my best attempt at drawing a sphere here. So I'm going to draw a circle in the YZ plane, close enough. And you can imagine, this rotates around. You can see it, it's there. Right, so we have this sphere in 3 dimensions. Right, or just sphere. And it has a center. We're going to say this has the point HKL. Now, obviously, I've drawn mine at the origin, but that's beside the point. Pretend it's not there. Okay? Now, the last piece of information that I need here is, well, how large is this sphere? Well, so if I take my center and I draw it to any point on the sphere, you can pick. I'm just going to pick this point on the sphere. Right? And we're going to say the distance from the center to our actual sphere, we're going to denote with r, the radius. We've dealt with polar coordinates not too long ago, so this is just r. Now think about what's happening here. This is just the distance from our center to some xyz value. And I'm just going to label this xyz. Right, now we already uncovered the distance formula. I'm going to repeat it one more time. So we said the distance, and I'm just going to label them the distance from point A to B, and I'm going to leave it in the squared form, is equal to, well, we said this is the difference between the x values. We'll say this is x2. This is the difference between the y values. And the difference between the z values, right? This came from the Pythagorean theorem when we combine the 2 triangles together. Okay, so now let's just take our distance formula, which we already uncovered, and use this over here. So in this case, well, what is AB squared? This is our distance squared. What is our distance here? Well, our distance is our radius, So our radius squared. And now let's go ahead and just start replacing stuff. We have our x value, We'll just call this one x, minus our other x value, which we just call h squared, plus our y value, which is just some arbitrary y, minus our center y value, which we call k. And same thing, Our z value, some arbitrary z value, minus, we call it L. And guess what we have? The equation of a circle. So I'll do a quick example since this didn't go very long. You can imagine if I gave you some centers, so let's say the center is -2, +3, -7, and we have a radius of, let's say, 8, based off this information, right? It's just substituting in things, right? So r squared is 64 is equal to x minus a negative 2, x plus 2, plus y minus 3 squared, plus z minus a negative 7 squared. And that's it. We're done, right? So we have our center and we have our radius. Easy enough, right? Equation of the sphere. So as long as we know where the distance formula is coming from, the derivation of the sphere is the same, right? There is no difference. Okay, coming up, we will go through a bunch of different examples now that we've covered all the content. I will see you guys in the example videos. All right, now time for some actual examples. So these ones will be fairly quick. I'm going to give us a point. So we'll say 2, -5, 4. And what I want us to find with this point is the distance. All right, so these are all distance questions. And we'll call this point A. From A to, let's say, the xy plane. Right, so what's the distance from A to the xy plane? Maybe we'll do A to the yz plane. And you can write plane. And we'll do, let's say, A to the x-axis. Okay? So, right, let's think for a second. A to the xy plane. How do I take the distance from a point to a plane? Well, if you drew this, so let's go ahead, we'll draw this. We'll do our best attempt, let's say, at drawing. We at least want to get one visual here. And so we have, kind of hard to plot points in 3 dimensions. We have 2, so positive 2, 1, 2, -5 in the y, 1, 2, 3, 4, 5. So it's somewhere out here, right, where these two things overlap, and positive 4, 1, 2, 3, 4. So here, then here, so somewhere here. All right, so we have this point A. And I want to know the distance to the xy plane. Right, well, the xy plane, you could think of it kind of, right, this is the xy plane here. It's a decent xy plane, right? And I want to know the distance to the xy plane. Well, I can just draw it straight down, right, to the xy plane. So what does this end up being? Right, if I want to know the distance from A to the xy plane, I just draw a line straight down in the z direction, right? So the difference is just the difference between z's here, right? Well, my z here, right, I have 2, -5, and 4. And in the xy plane, what's my z value? Well, my z value is 0. So the distance between 4 and 0, right, is just going to be 4. Right, so if I'm drawing it down to the xy plane, right, I just need to look at the distance between my z values. That way I can get down to my xy plane. And so you can imagine the same thing here. I won't try to draw the yz plane, but if I'm just in my yz plane, I draw the distance down from my x's, right? My x's are at 2. They need to get down to 0 because at my yz plane, my x values are 0. So the distance between my point A and yz plane is 2. Okay, so those two not so bad. What about A to the x-axis? Right, well, my x-axis is what? It's when my y's equal 0 and my z's equal 0, right? So you can write that out. For your x-axis, think about if we're just traveling along my x-axis, my y values aren't going any, or my x-axis, sorry. My y values aren't going anywhere, my y value is 0. And my z values aren't going anywhere, my z value is 0. So we need to take the distance of our y and z, right? So in order to find the distance of our y's and z's, we use our Pythagorean theorem, or our distance formula in 2 dimension. And I'm going to find the distance between my y, right, which is just going to be -5 squared, plus my z, right? My y value is 5 away from my y-axis. My z value is 4 away from my z-axis. All right, so you can imagine my point is here, right? And I want to get to the x-axis. Right, so let's say, a little hard to visualize here, but I believe the way we want to draw this is here. Right, so we're finding the difference of our z's, which is 4 and 0, right? And the same thing for y's, right? So again, Pythagorean theorem, or our distance formula in 2 dimensions, we end up with the square root of 25 plus 16, which is equal to the square root of 41. Right, so I'll leave this example here. Probably could have made the graph a little bit bigger. We'll go into a few more examples. Again, ask questions as you go, comment, etc. All right, see you shortly. Last example of the day, right? Equation of a sphere example. And I'm going to have the question pop up, but I'll write down what we have. Right, so the question is, if I give you a center of a circle, and let's say it's 8, -2, 4. And the question is, if I want this this sphere to only touch the xy plane once, what would my equation of my sphere be? Right, so I'm given a center. I'm not given the radius, right? That's kind of a key on what we need here. And I only want this to touch the xy plane once. Well, first, let's go ahead and write out some information that we have. We have everything about this sphere except for one piece, right? So I know for the equation of a sphere, x minus 8 squared plus y plus 2 squared plus z minus 4 squared is equal to, well, that's the part that we don't know, right? We don't know that it's equal to. And I should also have a graphic that's been hanging out over here. Okay, the only thing I know is that it touches the xy plane once. Right, it touches the xy plane once. If it goes past the xy plane, it's going to touch more than once, right? So think about what the radius would have to be, right? If I'm touching my xy plane once, that means my z value here in my xy plane is equal to 0. Right, so I want my z value, I want to touch z is equal to 0 one time, only once, right? So that has to do with my relationship to my radius, meaning, right now I'm at a z value of 4. I need my z value to only go down to 0, right? So my z value right now is equal to 4, and it can only go down to z is equal to 0. Well, what is this? This is telling us the relationship of our radius. My radius can only be length 4, right? Because it can go down to z equals 0, but we don't want it to pass through. If it passes through, we're going to touch the xy plane more than once, right? So this is telling us the distance between my z values can only be 4, or my distance is 4, so my radius can only be 4, right? So this tells me my radius is going to be 4. And because of that, right, this is radius squared, which means this is 16. Right, so that's all it is. It's a little bit of critical thinking, right? I give you the center. I go, what information do I need to have the equation of the sphere? Well, I need it to be 16, I need my r, right? And I go, well, if I only want to touch the xy plane once, that means that's as far as my radius can extend. And if I'm just in my xy plane, right, that's where z is equal to 0. We found the distance between z is equal to 4 and z is equal to 0. That's our radius. We took our radius squared. Hopefully the depiction over here helped. that is it. That is all I got for you guys today. If you have questions, comments, suggestions, leave them down below in the YouTube link or ask in class. All right, thanks everyone.